related to ICCF 24.
Good morning, everyone. Thank you so much. I want to make sure, am I coming through okay?
Very good.
All right, wonderful. So I wish I could be there with you in person this year, maybe next time, but the virtual option has been wonderful. Thank you so much. And I congratulate the organizers for such a well-run conference this year. This morning, I'd like to talk about overview of LENR products, and in terms of lattice confinement fusion, fission, or both. And I'd like to acknowledge my co-authors, Pamela Mosier-Boss, Lawrence Forsley, who was speaking a couple days ago, Wayne Jennings, Bruce Steinitz, Gus Freilich, and Robert Hendricks. I'm trying to advance, oh, there we go. So here's an outline of my talk. I'll give a very brief overview of LENR products. We all know what they are, and a little refresher on what lattice confinement fusion is. And then I'm going to talk about 3 sets of experiments that we have conducted, and in terms of briefly what they were and the products that we detected on each of them. And then I'll put forward some transmutation theories and end with a summary. So as we all know and have seen this week, there's many different fusion reactions possible, and I like to term this talk about this in terms of a nuclear soup, for example, because some of us may concentrate on one of these or a couple of these reactions, but they're all happening pretty much all at the same time in different probabilities as listed here. And in terms of lattice confinement fusion, there are 2 parts and a trigger that are needed for fusion to happen. And we've heard a lot about electron screening this week, and that increases obviously the probability of fusion happening and the high fuel density that is needed to have, again, raise the probability of these things happening. And then a trigger is that needed to set everything off. So in lattice confinement fusion, we obviously have a lattice of metal atoms that have a sufficient amount of electrons to offer for electron screening. And certain metals can hold the deuterium better than others, and we've investigated a few of those, or several of those. And in our experiments, we determined that inside the lattice, that is where, the higher kinetic energy is happening, and yet the whole lattice keeps to be room temperature. So during our Bremsstrahlung experiments, we conjectured that some of the deuterons in the lattice were photodissociated, and high energy neutrons were present. And with the presence of electron screen here, the 2 deuterons have a higher probability of fusing together. So there's a little animation that shows you what we think goes on in that lattice. And then the bottom is a depiction of our theory work conducted by Vladimir Pines and his late wife, Mariana Pines. And we have determined that we can get up to 10 to the 20th increase in fusion probability, depending on the potential. So the first of the 3 experiments I'll talk about, the gas cycling experiments. I talked about this at length last year, so I just want to give a refresher of what the experiment was all about. And it was conducted by Gus Freilich, who was inspired by the electrolytic wet cell experiments of the time, but knew that you needed the deuterium and the palladium, but he was working with a hydrogen purifier at the time and decided to try out some things, and he was surprised to find that he was getting some temperature rises that weren't explained by any other means, by cycling deuterium gas in and out of this palladium silver purifier coil. So some of the byproducts of those experiments, when we did bulk analysis of the palladium silver tubing, we detected elevated levels of chromium, copper, iron, manganese, and zinc. Most notably, the chrome and the manganese and zinc were not detected in a control or unexposed piece of tubing, but they definitely were, with a very high increase in zinc. So I was very, very curious. So we also looked at the surface of an unexposed and exposed tubing, and we first saw the unexposed. It's mostly palladium silver, as you would imagine, and with trace amounts of other elements such as iron, silicon, and aluminum. Whereas in the exposed tube, there were some spots that were detected on this one piece in particular, and also saw iron, chrome, copper, and an overall spread of zinc, very similar to what the bulk analysis showed. Now we created a trench with gallium ions. You see that, that here. And that was used to identify the spot, and we did tough SIMS analysis. Here's some EDS elemental pictures of this area, and you can see definitely the spots of iron, copper. So this was all very interesting. So to do the goal of the tough SIMS was to see if we could identify whether these isotopes occur in natural abundance or not. If they didn't occur in natural abundance, then we really, have stumbled upon something that's very, very unique. This is just an overview of what the palladium isotopes look like on the sample. You can see there's no silver in these darker areas. And similar with the palladium in these areas, but those are areas where these elements were found in these isotopes. So again, very, very similar to the other two analyses that we did with this tubing. So how can this occur? And we've got a couple theories about that. But first, I'll talk about the other two experiments that I want to touch upon today, and this was the Bremsstrahlung irradiation experiments. This work was published in PhysRevC about 3 years ago, and our objective was to investigate volumetric screening of deuterated targets, and we exposed them to a range of gamma beam energies from below the deuterium photodissociation all the way up to about 3 MV. And there's our wonderful team that conducted all the experiments there. And here's a diagram of the whole facility. And in this little tiny area here, that's where the target was, the breaking target, and our samples were positioned underneath this beam that swept back and forth. It's a dynamitron that we conducted the experiments with. So we did a lot of neutron spectroscopy with these experiments. That was something that we felt was really needed to look at what the energy levels of the neutrons that were being produced in our experiments. We knew they were being produced by other LENR experiments, but we wanted to characterize the energy of them. So our exposure of deuterated titanium and deuterated erbium to a 2.9 MV beam resulted in DD fusion and higher energy neutrons, which was kind of a surprise. So as I explained before, the energetic neutrons will transfer their kinetic energy to the stationary deuterons and then energize deuterons, and with electron screening, fusion can happen. Now we also think, because of the higher energy neutrons we detected, we either think subsequent fusion reactions took place due to the boosted or the Oppenheimer-Phillips neutrons. Let's see, we also did a significant amount of getting rid of the gamma, because we also, with this, we had to do some pulse shape discrimination and throw out some of the data to get a high statistical significance. In another experiment where we had a different facility that we had a 6 MV beam, we did exposure with deuterated depleted uranium. And we looked at the samples on a HPGE gamma spectroscopy system, and we, let's see, here the blue is the material before exposure, and then the black is after exposure. And we detected fission products, such as those listed there. So that was quite interesting as well. So the last set of experiments that I wanted to talk about this morning is the electrolytic wet cell experiments. We used a variety of detection systems. The one used here in this paper I referenced was evaluating bubble detectors as real-time dosimeters, monitoring the co-deposition process. And for the current set of experiments, we have used the neutron spectroscopy to evaluate neutron product energies and determine if there are any neutron emissions above background. So here we exposed the system to low electric currents, less than 500 milliamps, and we were able to find that we did have, but not of high statistical significance yet, DD fusion and possibly higher energy neutrons. And in designing the experiment, I used MCMP to model what type of experimental setup would optimize us the detection of the neutrons. Here in the middle, the dark blue is our Elgin 309 detector, and then the light blue is the cells around. I did 2 different size cells that we had available and various numbers of cells to determine that a 6 and the smaller cell, as shown here, was the optimum design to detect the neutrons. So here is a little depiction of a previous experiment on the resulting CODEP layers. You can see it's a very nice deposition there. And then just a timeline of our current experiment of what one of our cells looks like. It takes about 2 weeks for all the palladium and lithium and chloride in the solution to deposit onto our gold cathodes. And so we're currently running this experiment right now. From a previous run, here's some neutron spectroscopy. Again, still, it's not highly statistically significant yet, but we believe we have detected it. This graph here is the experimental minus a background set of data, and we do see indication of 2.45 MeV neutrons and possibly even higher. Let's see. This also we discovered in the last run was the pathway to fusion scaling. In that last experiment, we periodically rebuilt the nuclear active environment by adding additional electrolyte solution. And after the first 2 hours, we had a neutron spectroscopy spectrum that looked like this and indicated that there was some higher energy neutrons even here, in addition to the 2.45. And then after the second, taking just the third 2 hours of data, those higher boosted fusion energy neutrons seem to disappear, and the DD fusion neutrons take over. So we're further investigating this as again, a pathway to fusion scaling. So we did some SEM analysis on the cathodes afterwards, and in some instances, we found some very interesting products that weren't with the starting materials. For instance, here we have calcium peroxide spots that we detected on the surface of the CODEP layer. They actually look like little cubes on top of the cathode. So it was another indication that we have some transmutation going on here. So there's another spot there with, again, calcium peroxide. So how can we get all of these products that I've shown you from our experiments? Well, several researchers have looked at the possibility of these materials being fissioned, like Takahashi wrote about possible photofissioning of palladium, where they detected pairs of products such as iron and calcium and titanium and chromium. And they believe that it was a nuclear excitation by low energy, high flux photons in their electrolysis experiments. So could we be maybe fissioning fused DPD or deuterium silver products that have turned into unstable silver or cadmium? Now, going through the investigations, a colleague of mine, one of the co-authors of mine, Bruce Steinitz, we looked at the pairs that were possible with the unstable silver or cadmium products. And we split them up into one of them as a stable pair, and then determined that the remaining element would undergo beta decay many times to a stable isotope. And then we determined the isotope pairs that we actually also observed in post-tests, such as iron and titanium, manganese and chrome, and iron and chrome. So another aspect, another researcher looked at how possible are these elements such as palladium being fissioned, and they looked at this facility relationship, which was initially derived for characterizing spontaneous fission, and they determined that a relationship of Z squared over A greater than 17 would give you an indication that it's very possible to fission that element. So for instance, palladium 105 has a facility of 20.15, and silver 107 has a value of 20.65. So they're definitely potentially fissile. So, you know, traditional fission with elements such as uranium-235 and plutonium-239 are very easily fissioned with thermal neutrons, but for a palladium deuterium system, it will require much higher neutrons. It's possible with the absorption of a nucleon. So there's possibility of that absorption resulting in a release of 8 MeV binding energy, and it's shared as kinetic energy amongst the nucleons. And there also is possibility of the Oppenheimer-Phillips reaction, where you get a resulting kinetic energy of the proton of greater than 6 MeV. So, and then certain fusion reactions generate 14 MeV neutrons and 15 MeV protons, as we saw earlier. And, but the fission barrier is really, you know, really need a 40 to 50 MeV fission product. So, you know, it doesn't seem possible, but we end up seeing these fission pairs happening in our experiments. But one thing that's interesting is that palladium 105 has an oblate nucleus, so maybe that has something to do with it, where it's more easily fissioned in that way. So here's some examples of some.
Sorry.
Okay.
5 minutes.
Okay, thank you so much. So this is just a representation list of pairs that we found that were possible. They conserve energy and spin and parity. So this was a, you know, the possibilities here. There's additionally some more with fissioning of unstable isotope cadmium. More recently, we're looking at a hybrid fusion fission process. And so here we can take advantage of both of these processes, where the fusion reactions provide neutrons in various energies and to fission non-fissile materials such as natural uranium and thorium, and depleted uranium as well. So we're currently investigating that under a NASA Innovative Advanced Concepts Fellowship that we were awarded, where we're looking at using a fusion fission reactor to power a autonomous robotic probe to drill down underneath icy worlds of Enceladus. So let's see. So we're very excited about that work. So in summary, we have observed transmutated products with various different experiments with the deuterium gas cycling of the palladium silver alloy. And we also detected fusion and higher energy neutrons and fission products with our Bremsstrahlung irradiation experiments, and transmutations observed on the electrolytic wet cell co-deposition on cathode wires. And obviously electron screening greatly reduces the Coulomb barrier, facilitating the capture of deuteron or proton capture of palladium or silver, which we believe encourages the fissioning of those products. And, but, you know, there's still yet other unknown vehicle that assists with the fissioning of the unstable isotopes. But we've determined that many fission pair possibilities exist. And of course, additional experiments are needed to confirm the working fusion-fission process. So, and finally, I'd like to acknowledge a couple of my team members who were very instrumental in analyzing the neutron spectroscopy data, and our research funding has been provided by a couple of places at NASA at headquarters at the Space Technology Mission Directorate, with the NIAC award that I mentioned, and with the Science Mission Directorate also there with the Planetary Science Division and the Planetary Exploration Science Technology Office. So thank you so much, and I'll take some questions now.
Thank you, yes.
Hello, this is probably already very early in the United States now.
It is very early. But thank you, Conrad, for organizing such a wonderful conference. Everything turned out well.
Thank you. It's a pity that you couldn't come here personally.
Yeah, I know. I wish I could have.
Yeah, my question is, or maybe a more comment, you know. This was very nice, very exciting experiment using Bremsstrahlung, and it was a demonstration that fission and fusion can take place at the same time. But yes, of course, Bremsstrahlung and you know, very high flux Bremsstrahlung is completely different situation if you are speaking about thermal energy called fusion you know, environments. And therefore, I have another idea to maybe to think about fission at thermal energies. I was always against about it because, you know, from the theoretical point of view, physical point of view, it is very strange to understand it. It is very difficult to think about it. Yes. But the point is, you know, we discussed already yesterday about it. We have discovered a year ago large new reaction channels in DD reaction. Production of electrons and positrons, very high energies, up to 24 or 23 MeV.
Wow.
And then compared to, you know, to gammas, the stopping power is really large, and this an interaction with the matter is much better than gammas. Another point is, of course, we couldn't see any gammas in the experiments up to now, and therefore electrons or internal pair creation we have discovered a year ago, and we presented this year new results with very high statistics. It is, I think, very convincing result. And the final conclusion is that thermal energies, this channel could be 100 times stronger than a proton channel, DP proton channel, which is a usual thing. And neutrons at thermal energies should be even much weaker than protons. So if you take into account that we have high energy electrons that can locally interact with small or surrounding of the first DD reaction, you know, this is probably possible to think about fission as well.
We're almost out of time, Comrade.
So this, you know, photofission is known for many years, and fission, because of high energy electrons, is also known for many years. So maybe there is a direction we should think about to understand something. Okay.
Yes. Thank you very much. Yeah, that's exciting. Yeah.
Do we have any more questions? But
Thank
make
you.
it brief, Bob.
Are you aware of the work at Moscow Nuclear Physics Institute of Bogdanovich et al.? 2 pieces of work: plasma flow discharge produced birdies on X-rays, and a synchrotron accelerated electrons into a conversion target going through a magnetic field, removing the electrons, and on there they see exactly the same birdies. And these are broken up clusters that can persist for 2 days in material, and they are able to transmute material because they have closed Poynting vectors.
Very interesting. No, I'm not aware of that work. I'd like to learn more about it.
Okay, so I will send you the relevant papers. Video
Wonderful.
recordings of long-lived plasmoids. Go look it up.
Okay, wow.
Thank you.
Exciting.
Thank you, Bob, and thank you, Theresa. That was a
All right.
pretty spectacular amount of work you've done there. Yeah.
Oh, it's not, it wasn't me alone. My team is wonderful.
I can imagine. Okay, I think a round of
Thank
applause
you.
would be good.
Thank you so much.